Thanks everyone, and welcome to our weekly seminar. Today we're very pleased to have with us Professor Frank Ball, and he's going to be talking broadly about epidemics on networks. Frank is a representative of a fair number of people in the probability community who have recently, or over the past few years, become more interested in network models that are slightly more sophisticated than the kind of baseline SIR situation. And I know one of the things you're going to talk about in this talk is extending the study of epidemics to networks that have tunable parameters for things like clustering and correlation. So it's very exciting work. There's plenty to read on the archive, and I'm sure Frank is going to tell us more. Thank you.
Okay, thanks so much, Patrick, and thank you very much also for the invitation to be part of this program. It's very exciting, and it's a great pleasure to be here. So in this talk, I'm going to really describe two pieces of work. One is going to be concerned with epidemics on networks where you also have casual contacts, and the second one is going to be concerned with an epidemic on a network with tunable clustering and degree correlation. The former is joint work with Peter Neal, who's now at Lancaster University, and the latter is joint work with David Sirl and Tom Britton, who's in Stockholm. Okay, a brief introduction. Sort of classical epidemic models usually assume that the population the epidemic is spreading in is homogeneously mixing, and it consists of homogeneous, all individuals sort of behave according to the same probabilistic laws. However, it's important to include individual heterogeneities and social structure so that models better reflect reality. An assumption of homogeneous mixing is far from what one sees in real-world epidemics. And over the last 2 or 3 decades, there's been a lot of interest in models for epidemics among structured populations, which incorporate realistic departures from homogeneous mixing, but at the same time retain some level of mathematical tractability. And one class of such epidemics is epidemics on random networks. And I just said I'm going to talk about 2 extensions of the standard SIR epidemic model on the configuration model network. So the basic idea is you've got a network here of some random graph, and you have an epidemic. I'll explain what an SIR epidemic is later, but essentially in the standard model you can only infect your neighbours in the graph. And I want to sort of look at 2 extensions. Well, one extension of that is sort of casual contact. So in reality, I mean, typically these sort of edges refer to friendships, but it's quite likely you will infect somebody on the train or something like that who you have no connection to at all in the graph. So that's one extension I'm going to look at. And most of the early work, this graph is actually a configuration model network, and that has no sort of clustering or degree correlation. And I'm going to describe a model where you've got tunable clustering and degree correlation. Okay, so the first piece model first. It's going to be a standard configuration model network to start with. I'm not sure I need to go in great detail. Capital D is going to be the degree distribution. You sample NIID copies of D, conditional on it being even, or you can just throw one away, and you attach DI half edges to each of these individuals, and then you pair these half edges up uniformly at random, and that gives you a network. There'll be some imperfections in the network, like sort of self edges and parallel edges and self loops, but if the variance of the degree distribution is finite, they become sparse as the population size n tends to infinity. Okay, the epidemic model is what's known as SIR epidemic. So this is something like, for example, a single season of flu. You start off being susceptible to the disease. If you have close contact with an infective, you become infected. And in this particular model, though, you're then immediately able to go and infect other individuals. You remain infectious for a while, and then your infectious period ends, and then you're immune to any further infection. All the results I'm going to describe today are concerned with the final outcome of such an epidemic. and they're actually invariant to assumptions about a latent period. So the fact you can immediately affect other people doesn't matter as far as the results are concerned. The infectious periods are going to be IID and follow some arbitrary but specified distribution I. And if infected, an individual, little I say, makes two types of contacts. It makes local contacts along each of the DI edges emanating from that individual in the graph at rate lambda L, and global contacts at rate lambda G with individuals chosen uniformly at random from the population. So these are rates of Poisson processes which govern these contacts. So the second set I'm going to call casual contacts. So if I set the rate lambda L to be 0, I just get a standard homogeneously mixing SIR epidemic because there's no spread in the network. If I set lambda G equal to 0, I get a standard configuration model SIR epidemic. Okay, here are some simulations of that model. I'm not going to describe them in great detail, but this is the final outcome of such a model. At the top row, you've got a population of size 250 individuals, and the bottom row of size 1,000 individuals. This parameter R0, I'll explain it later, it's a sort of threshold parameter. If it's larger than 1, then it's possible to see a large outbreak. If it's smaller than 1, then you typically only see small outbreaks. And so when R is large, R0 is larger than 1, you get this sort of bimodal distribution. Still, even though it's above threshold, there's quite a still high probability that you may not see a large outbreak. And you see, as you increase the population size, the distinction between, I mean here, it's not clear whether that's a small or a large outbreak, the distinction between these two scenarios become clearer. Okay, what are the sorts of questions that we're going to look at? Suppose you start with an epidemic with few initial infectives, then is it possible for the epidemic to become established and lead to a major outbreak? So that's the role that can be played by this basic reproduction number R0. If it is possible, what's the probability of a major outbreak? If a major outbreak occurs, how large is it? Some sort of law of large numbers for it, and also a central limit theorem for the size of a major outbreak. What is a major outbreak? Well, I've given one definition here, but it's perhaps not the best. It's an outbreak which affects at least log n individuals. I mean, when I first talked about this stuff, I didn't actually give this definition at all, and somebody asked me what a major outbreak was, so I gave this definition. They pointed out that log n wasn't very big. So I can easily make this up to n to the gamma, where gamma is less than a half. And in fact, a major outbreak is always going to be of order n, but the constant depends on the parameters of the model. Okay, so let us assume that n is large, you've got few initial infectives, then you can approximate the early stages of the epidemic, or the process of infectives in epidemic, by a two-type branching process. So you've got type L individuals, these are infectives which are infected locally through the network. You've got type G infectives, and they're infected globally by a casual contact. And early on, because these sort of global contacts are occurring uniformly at random in the population, it's very unlikely that you'll contact somebody who's previously been infected. And similarly, because the way in the configuration model the network was formed, it's very early on in the epidemic, it's unlikely that, again, you're going to infect somebody who's previously been infected. So that means the process of infectives can be approximated by, in this case, a two-type branching process. And the mean offspring matrix of that branching process is given here. So MGG is the mean number of global contacts that emanate from somebody who is infected globally. Well, their mean infectious period is mu I, and they make these global contacts at rate lambda G. So that's that element there. And similarly for somebody who is infected in the network. What about the network contacts? Where somebody was infected globally, all you know about their degrees, it comes from the standard degree distribution D, and so the mean number of contacts it makes is just given by PL times mu D, where PL is just the probability that this individual infects a given neighbour. And if it's infected through the graph, through the network, then this individual has a usual size bias degree distribution. So you replace mu D by mu D tilde minus 1. You lose 1 because one of your neighbours is who is infected. then R0 is just the maximum eigenvalue of this matrix M, and the probability of major outbreak is strictly positive, and the limit as n goes to infinity if and only if R0 is greater than 1. Okay, and this can all be made fully rigorous using the coupling arguments. What about the end of the epidemic? Suppose you've got a major outbreak, how large is it going to be? We can work this out. One way of working this out is by looking at a digraph of potential local infections. So what we do here is we take every individual in the population and we ask the question, if that individual becomes infected, who would they infect locally? So we draw up a list of who they would infect locally, and then we draw a directed graph from that individual to all the individuals they would infect locally. And we do that for each individual in the population, and you end up with a graph, which in this example looks like this. Okay, and then we can construct what we call a susceptibility set of individual I. So we take individual I, and this susceptibility set is this collection of blue individuals. It's all individuals that, if they were becoming infected, would infect individual I by a chain of infections. So all individuals that can be reached to I by a chain of directed arcs. So in this example, it's all these blue individuals.
So there are cases like the bottom left where you can infect somebody, but they can't infect.
That's right. Yeah, it's a directed graph. I mean, if it, I'll be a bit careful here actually. If it's a constant infections period, in some cases you can replace this directed graph by an undirected one because you're only ever going to lose one link. But if it's not a constant infections period, then there's dependencies in the presence of arcs coming from an individual. Okay, and if you think of the epidemic model, this individual I will be become infected by the epidemic ultimately if any individual in this susceptibility set is contacted globally, or is the initial infective. When they be contacted globally, then it will lead by a chain of infections to that individual being infected. Okay, so we can now draw up a sort of informal derivation of the final outcome of this epidemic. So let's suppose that n is large and there's few initial infectives, and a fraction z of the population, z is the expected proportion of the population was infected by a large epidemic. Then pi is the probability a typical susceptible avoids global infection. Well, if a fraction z are infected, there's Zn individuals roughly infected by the epidemic. They each have an average infectious period of length μi, and they're contacting this individual at rate lambda g upon n. So the probability an individual avoids infection, the limit would be e to the minus lambda g z times μi. So 1 minus z, that's probably is just probably a typical susceptible avoids infection by the epidemic. That's the same as the probability that a typical local susceptibility set avoids infection. So we just condition on the size of that typical local susceptibility set, and we get this expression here for 1 minus z. So this is just a PGF of S. I'll explain what S is later, evaluated at this parameter pair. Then if you look at x as 1 minus z, you can recognize it as an extinction probability of a Galton-Watson branching process, which has this sort of Poisson offspring distribution of a random mean with lambda g mu I times s. And if R0 is less than 1, then the only solution of this equation is 0, but if it's greater than 1, there's a unique second solution, which gives a fraction of individuals infected by a large epidemic in the limit as n goes to infinity. Okay, that's a sort of heuristic argument. It can be made fully rigorous. I'm just going to outline now how we make this argument fully rigorous. Okay. So let's first look at this. Let Sn be the size of a typical local susceptibility set. Okay, and I'm going to use sort of script S for the set itself, and sort of bold, just S, Roman S for the size of the set. And then AIN is going to be the set of neighbours of SIN in the network. So these are people who are neighbours of people in the susceptibility set, but they don't actually join the susceptibility set, because they wouldn't, if they were to become infected, they wouldn't infect these individuals. Well, one can form the network, i.e. pair up the half edges, as we construct this process on a generation basis. And using a coupling argument, you can show that this process tends to a two-type, these values tend to the total progeny of a two-type branching process, with type 1 individuals corresponding to those which join the susceptibility set, and type 2 individuals being those in the neighbour of the susceptibility set. And only type 1 individuals are going to produce offspring. The total number of offspring of the initial type 1 individual is distributed according to D, and of successive individuals, type 1 individuals, is D tilde minus 1, where that's a size bias sampling. And each birth is type 1 independently with probability PL. So that's the probability that a neighbour infection in this network. And because you're looking at different individuals, these neighbours are independent. So this happens independently. If you look at the forward process, that's not the case. Okay, and the asymptotic proportion of the population affected by a major outbreak is given by the large, as I explained, the largest root of that equation there. Okay, I'm going to give a slightly different way of constructing this model. So I can construct realization of the final outcome of this epidemic EN as follows. I use this directed graph of potential local contacts to model local infection. And to model global infection, I'm going to have a set L1 up to Ln of IID exponential random variables of rate lambda g. And I assume that each susceptible accumulates exposure to infection, global infection, at rate n-1 times the number of infectives present. And that individual becomes globally infected when its total exposure to infection reaches its critical level Li. And because all these things are happening at points of the Poisson process, this gives you another description of that model. And I'm going to construct a related epidemic. It's not quite the same epidemic. So I'm now going to suppose that each individual in the population is exposed to T units of global infection. I'm going to use these critical levels L1 up to Ln to determine who is infected globally. And then I'm going to let those people who are infected globally via this graph of potential local contacts determine who is infected locally. So if chi-in of t is the indicator function of whether individual I is ultimately infected by this epidemic, then for it to be infected, somebody in its susceptibility set must be infected. So the minimum over its susceptibility set of all these LJs must be smaller than t, otherwise it's not infected. So the expected value of chi-in is just the expected value 1 minus expected value of 1 written down there, e to minus lambda g t sin. So that's given by that PGF expression again. I'm going to let Rn of t be the sum of these chi-in of t's over the whole population, and An of t be the sum of these chi-I of t's times the infectious period if they become infected. So that gives you the total amount of infection in this epidemic model. Okay, I can now construct a realization of the final size of the original epidemic as follows. So I suppose that the whole population is initially, each individual is exposed to T0 bar n, which is n to the minus 1 T0 n units of global infection. Okay, so start off here. Then this initial exposure to global infection may infect some people and create further global infection. And that amount of further global infection would be An T0 bar of n. So this is just averaging it, so I get T1 bar of n is just T0 bar of n plus n to the minus 1 An of T0 bar of n. So where are we? So it goes up to here, then it goes up to here, then it goes up to here, then it stops. And this process must stop in a finite, after another finite number of steps, because the population is finite. And when it stops, t infinity bar of n, which I call here, is just given by this expression here. And Rn of t infinity bar n is just that sum there, gives you the final size of the epidemic, and the final severity is given by that expression there. Okay. And I'm not going to go through this in great detail, but I will say a bit more about it. What you can do now is you basically you look at a law of large numbers by just looking at the average, working out what this this A bar process converges to as n goes to infinity. It converges to some deterministic function, and then you can therefore use that to show the get a law of large numbers to the final size of the epidemic, and then you can look at fluctuations about this AN process, and after quite a bit of work, a lot of work in fact, you can get a central limit field. So I'm not going to go into details about it, but what I will say a bit about is how we actually work out the variance, the mean, the variance of this AN T process. Okay, so we want to work, I'll just work it out for Rn of T. So the mean of Rn of T is straightforward. It's just the mean of some of these indicator functions. By exchangeability, it's just n times one of them. And we've already seen that this indicator function is given by that expression there. So if we let n go to infinity, R of t, which is just 1 upon n times e of Rn of t, it's just 1 minus that limit, because I've already explained that Sin converges to S, it's just given by that expression there. So that's straightforward. What about the variance? Okay, we want to work out the variance of n to the minus 1, the variance of Rn of t. So that's, we want the limit there, and we can write it in terms of some of the indicator functions. These are all exchangeable, so I can write it in this expression here. So it's n times this variance plus n minus 1 times the covariance of 2 of them. We've already seen, it's easy to work out that limit there. It's given by that expression. So we need this limit of n times the covariance of 1 minus chi1 of n of t and 1 minus chi2 of n of t. Okay, if we look at that, then well, we can write down an expression for it quite easily. That's just, this is for them both to avoid infection, then the union of their susceptibility sets must avoid infection. You take off the product of the individual ones. And now we can condition on the size of the first one's of individual one susceptibility set, and also on the size of the number of neighbours of it in that susceptibility set. So we need to work out this expectation, well, this thing here. Okay, so we want that. Well, if we know the size of individual one's susceptibility set, an individual two we can imagine is just chosen uniformly at random from everybody else in the population, then the probability lies in susceptibility one susceptibility set is just given by S1 n minus 1 upon n minus 1. And in that case, S2 minus 1, there's no extra individuals added to the susceptibility set. So if we do that, we end up with this sort of thing here. We want an n out the front. This term here comes from this stuff here, and you end up with you want to work out this expectation here in the limit as n goes to infinity. Okay, generally this is rather tricky to do, but in the case where the degree distribution, and it can be done generally, but I'm just going to outline how we do it when the degree distribution is constant. So everybody has D neighbours, and the infectious period is also constant. Then we can construct this first susceptibility set as before, but we leave the half edges corresponding to these ones that don't join the susceptibility set, this A1n, we leave those loose. Then I construct the susceptibility set with, well, S2n minus S1n on a generation basis, continuing to form the network simultaneously. If the half edge is paired with the loose half edge, there is no individual, because if it's paired with the loose half edge, that just joins the previous susceptibility set. And so it doesn't provide somebody in this set difference here. Okay, and now as n goes to infinity, this process here converges to a branching process, which I'll call BP alpha n, in which each birth is aborted independently with this probability here. If I let, if I use psi of xa be the PGF of this branching process, of the total progeny of this branching process, if I put alpha n is naught, alpha is naught, I just can end up beside the susceptibility set. If I can work out this limit, then it turns out you can express it in terms of the derivatives of this, I've lost it now, of this thing here. At the end of the day, you end up with an expression for this limiting covariance you want. If the degree distribution isn't constant, it's much more complicated because you've got to take account of which of the degrees of individuals you've actually used up in forming the first susceptibility set. Okay, well, similar methods to this can actually be used to work out the asymptotic variance of the giant component in configuration model random graphs. I'm not going to go through any details at all, but I mean, essentially what you can do, if Rn is the size of a giant component, then we know that Rn, if it's supercritical, then Rn upon n goes from probability to rho, say, where it's given by this expression there. So if you let Un be the number of individuals which aren't in the giant component, then clearly the variance of Rn equals the variance of Un. But instead of looking at Un, we look at the number of vertices which are in components of size less than n to the beta, and in the limit that has the same, have the same thing. And then one can use similar methods to what I've described, except now rather than forming susceptibility sets, you're looking at these components of two individuals, and at the end of the day, you end up with an expression for the variance of the configuration modeling random graph. And you get a different answer when we use prescribed degree sequences and mono-read random graphs, or if you use sort of the random graphs I've been describing with sort of random degree sequences. So these are the expressions you end up with for the variance, asymptotic variance of the giant component. So they're fairly simple in some sense. Okay, just want to give a few simulation results of the epidemic model. So what have we got here? So in this first, so we all have constant degrees actually. This first epidemic here, the local epidemic is subcritical. Here it's supercritical, and this is expect the degree of the infectious period is constant. In that case, the fraction infected by a large epidemic is the same as the probability of a large epidemic. And I've given some sort of simulation results and some theoretical results. And generally, you see that the asymptotic results are good for n is say about 1,000, and not too bad for n is 250. I've also got some results here where lambda g is 0. The theoretical ones there are heuristic. All I've done is let lambda g go to 0 in the previous variances I've had before. But in fact, it turns out, well, in some cases at least, that's not a bad approximation. Here's an example of an epidemic this is a standard SIO epidemic on a configuration model network, and overlaid is a normal approximation you get using that central limit field, which I say is not rigorous. Okay, so here's a graph of how the final outcome of the epidemic. So I've got two networks here, each with mean degree 8. In the blue curves correspond to a constant network where everybody just has 8 neighbours, and the red curves correspond to a network, a parallel network. The degree, I think, is less than 3, and so you're always going to see it's always supercritical. The solid lines are when you've got these casual contacts, and the dashed lines are when you haven't got casual contacts. So you can see that the effect, looking at it like this, at least the effect of the casual contacts is greater generally, unless it's highly supercritical for scale-free networks, sorry, for constant networks rather than for scale-free networks. And also, looking at it like this, the effect of these casual contacts can be quite significant. But this isn't really a fair comparison in some way because you're just adding these contacts in and you'd expect the epidemics to be larger. So what you can do instead, this is something done with a research student of Dave Sirl and Ben Davis. So what we've done here is we've actually fixed R0. R0 is fixed at 2, and vary lambda g. And but you vary lambda g between 0 and 2, so you move from the homogeneous mixing network to the one which is just a standard network model. In such a way, you choose, for a given value of lambda g, you choose the value of lambda, the network infection rate, so that R0 is 2. And if you do that, and this is what you get for various choices of the degree distribution. So now there's a big difference between what happens with, say, a power normal degree distribution and here a constant degree distribution. You get almost anything from 0 to 1 for the final size. These curves aren't monotonic. They are here probably monotonic, but in general, you can produce an example where they're not monotonic. It's fairly easy to see what happens initially. Initially, as you move away from homogeneously mixing, if the variance is smaller than the mean, you increase, and if it's larger than the mean, you decrease. But well, that's about the main results we have there. Okay, I now want to change track and talk a bit about this model with tunable clustering and degree correlation. Of course, there's numerous models for random networks that include tunable clustering and degree correlation. What we wanted to do was to find a model which allows for a wide range of tunable degree distribution, clustering and degree correlation, but also permits theoretical analysis of epidemics on those networks. I'll present the model we've used. This is joint work, as I said before, with Dave Sirl sitting there and Tom Britton. And essentially, we're going to put households or cliques into the network. Now, in epidemic modeling, households are important by themselves because a lot of spread of disease is within households. But here, I'm just going to use them as a device for introducing clustering into the network. So I'm going to use households or cliques to introduce clustering. And so these blue edges are going to be sort of local edges within households. And to try and tune degree correlation, I'm going to start off with I'll explain shortly, but essentially I'm going to pair up the half edges. So these global edges are going to be some sort of extension of the configuration model. And they're going to be paired up in such a way that will tend to induce correlation between neighboring individuals in the network. Okay, so I'm afraid I'm using little n now for a number of nodes rather than big N. I would have changed it, but I couldn't really change the figures very easily, so I kept with little n. So now you've got little n nodes labeled 1 up to n. To form the local edges, I just sample from some household size distribution, and the first n nodes I put into household 1, the next, H1 nodes, the next sort of H2 nodes I put into household 2, and so on, so the last household may have a truncated size distribution, and all nodes in the same household are connected to each other to form a clique. So the local degree of a node is just 1 less than its household size. Okay, what about global nodes? So what I do is we sample G1 up to Gn IID from some distribution G, which is the global degree of a typical node. And I attach sort of GI global stubs to these nodes as in the configuration model. We also attach IID labels, X, to the stubs, where X is just a Bernoulli trial with a parameter mod R, where so R is some parameter which belongs to -1 to +1, which is going to be used to tune degree correlation. Now I take all those stubs which have x labeled 0 and pair them up uniformly at random, like in the configuration model. I take the stubs that have x labeled 1 and I order them according to their total degree. So that's their local plus their global degree. Then I separate those stubs out into NQ equally sized quantiles. Then if R is larger than 1, we pair these stubs up within each quantile uniformly at random. So that's going to induce sort of positive correlation. If R is less than 0, we take the stubs in the kth quantile and we pair it with stubs in the NQ plus 1 minus kth quantile. And that will induce negative correlation.
Are you going to explain what the binomial 1R is? So what do you mean with the parameter being between -1 and 1?
Well, it has to be between -1 and 1 because it's a binomial distribution. So if R is plus 1, that means every global stub, so it is not, you don't pair any up uniformly at random, you would pair it all up within its own quantile, all of them are paired up within their quantile. If R is -1, all of the global stubs are paired up with somebody from the opposite quantile. If R is somewhere between -1 and +1, then some of the stubs are paired up with in the same quantile and some not. And if R is 0, then you're back to the configuration model. Okay, well, I'm not going to go. It's straightforward to work out things like the degree distribution. It's just a sum of the degree of its global degree and the household size of somebody who's chosen uniformly at random, -1. Clustering is straightforward to work out because in the limit as n goes to infinity, triangles only appear within cliques. So you get an explicit expression for the clustering. And the degree correlation is also fairly straightforward to work out. I mean, this expression's not quite so nice. You get this sort of, well, that's it there. But essentially what's happening is, well, to work out the degree correlation, you have to condition whether an edge is a household edge or a global edge. If it's a household edge, you necessarily got some positive correlation between the individuals at its end. If it's a global edge, then it depends on whether the X labels, etc. But it's not hard to work out what this degree correlation is. And so the degree correlation increases with R. So just give an example, a simple example. If you take a Poisson degree distribution, then we want a Poisson degree distribution with parameter gamma. We let G be Poisson with parameter gamma minus mu, and the household size be called Poisson plus with parameter mu. So that's a Poisson distribution conditioned on being strictly positive. Then you can just go into those formulae, and it turns out that the degree distribution is in Poisson, the clustering coefficient is given by that expression there, and the degree correlation is given by that expression there. And if R is 0, it turns out in this model that the degree correlation and the clustering coefficient are equal. And as R varies from -1 to +1, then the degree correlation varies between setting R as +1 and -1 in this expression. And you can do a similar sort of thing for any infinitely divisible degree distribution D. So in that example, if you look at the range of sort of values of C and rho you can get with this model, they're shown here. So if you've got just two quantiles, you get anywhere between this curve and this curve. And then as you increase the number of quantiles, you get a slightly wider range of parameters available. And in the limit, NQ equals infinity, that just corresponds to the case where if R is positive, you always pair up with somebody with the same degree. But although it looks like you're actually getting, even with NQ as 5, you're getting most of the space, there's actually quite a big, massive difference between the behaviour of epidemics when Q equals infinity and NQ finite. Okay, so we can now put an SIR epidemic model on this as before. I don't really now go through the details. Now lambda is just the rate at which you infect a given neighbour. So yeah, we've got simulations as before. Now actually, it's still splitting up into major and minor outbreaks, but it's not so, the distinction isn't so clear all the time. In fact, here it's not clear what's going on. You know, there's a very sort of wide range of possibilities. How much longer have I got?
Oh, you can go at least until 3. I think we started.
Okay, right, okay, yeah. Okay, well, we analysed this model in fairly similar ways to what we did with the previous model. So you can start off, here's an example network. Come from older talks, all the households are the same size, so don't worry about that. You now form a digraph of potential infections, like we did before, but now these are all the infections, not just the local ones. And if you look at the spread of an epidemic, suppose this is the initial individual, it will trigger a local epidemic in its own household, and then from that local epidemic, you may get, in this case, just one, you get one global spread, then trigger another local epidemic in this household, and so on. So if you look at it at a household level, you get a branching process of infected households. And this branching process is actually multi-type because essentially the type of an individual belongs, say, type I, it's either 1 up to NQ, and if I star is the primary case, or the first case in a household epidemic, single household epidemic, then the type is the total degree quantile of the stub used to form the edge from which it was infected. And then if you do that, you get this multi-type branching process. This parameter R star is just a dominant eigenvalue of the mean offspring matrix of that multi-type branching process, and you can work out an approximation to the probability of a large epidemic. And as usual, you can use a coupling argument to actually show that this convergence then goes to infinity. So look at the final size, we do a similar sort of thing. We now form a susceptibility set. So we start off with this individual here, and all these blue individuals, so people, if they were infected, would infect lead to that red individual infected. And you can construct the susceptibility set on a household basis, where you look at the local susceptibility set, you look at people from outside the household which will join that susceptibility set, and so on, and you get another multi-type branching process. And now it's much harder to show. In fact, we've only done it for, not for this model, but for a slightly simpler model. But you can approximate this susceptibility set process by that multi-type branching process. Then the limit as n goes to infinity, then the fraction of individuals infected by the epidemic is given by the probability that that limiting branching process survives. And you get a law, well, this is conjecture for this model, which you can prove for other models, you get a law of large numbers, etc. Okay, so just a few simulation results. So what we've got here, for various choices of clustering coefficient and parameter R, which controls degree correlation. I think these are Poisson networks, for example, we had before. The solid lines are the lines you get from the asymptotics and the branching processes. And these are sort of confidence bounds, mean plus or minus 2 standard errors from simulations. So I think there's 10,000 simulations to each choice of R. And which way around is it? The red ones are for a network of 10,000 individuals, and the blue ones are for a network of 1,000 individuals. So generally, the asymptotics are reasonable, you can see a sort of bias, clear bias for large and small values of R in these results of final size. That may be due to sort of imperfections when forming the network. So here we look at the dependence of well, it's probably a major outbreak because I'm using a constant infectious period. It's also the size of a major outbreak on R, PI, and C. So these are just different choices of a clustering coefficient. Remember, R controls the degree correlation. So roughly speaking, what seems to be happening, if the disease is well above threshold, the degree correlation does not have a massive effect on the outcome, but the size of the epidemic tends to sort of decrease slightly with increasing degree correlation. But if the epidemic is just above threshold, then the degree correlation has a larger effect on, a more significant effect on the outcome of the epidemic, and it increases with degree correlation. And if you look at this graph here, it's not obvious in this picture, but it's actually not monotonic. And if we look in more detail here, so there's not much clustering here. But now, as you increase R from -1 to +1, first of all, the size decreases, then it increases, then it decreases. And in fact, here, it's not even supercritical in a range. So you've got this rather sort of strange behavior on degree correlation. Okay, one final picture. So what we've done here is we've taken this model and we want the clustering to be degree correlation, I think it's about 0.2, and we can look at it. What happens is we vary from a clustering coefficient of whatever it is here down to 0.2 just by changing the parameters of our model so that the degree correlation is kept fixed. And if you do that, you get this this blue curve here. As you increase the clustering, you decrease the size of the epidemic. The red curve, what we've done here is you start off with this model here, and then you just rewire some of the households. So you take a fraction of the households, and then you break all the sort of edges within that household, and label them by the household size. And those ones which you've broken, you then pair up uniformly at random with with edges from other households of the same size. And that has the effect of reducing the clustering, but not changing the degree correlation. And if you do that, then as you move from this level of clustering down to almost no clustering, you get this red curve here. So even though the two models had the same degree distribution, clustering coefficient, and degree correlation, they have rather different final outcomes. Okay, so just a few concluding comments. Generally, the asymptotic approximations are fairly good for moderately sized populations. All these features we've been looking at can have a significant impact on disease dynamics. And then if you want to try and control a disease, it's going to have an impact on the performance of various mitigation strategies. As I mentioned, as you increase clustering, you tend to decrease the spread of disease. The effective degree correlation, for this model at least, is appreciably greater when the disease is close to threshold than when it is well above threshold. But as we've just seen, there exist distinct networks having the same D, C, and rho, such to have rather different epidemic properties. So obviously one has to be very cautious if you want to extrapolate to real-life epidemics. Okay, I'll finish there. Thank you very much.
to extrapolate to real life network, you actually want to fit. And one of my, I know Ben Cowling in Hong Kong has done quite a lot of data collection on households and spread of flow.
Okay.
Is there much connection between the data collection and these nice models that you've got?
Not as much as there should be. I mean, there's some, there is some connection, but not by me, I'm afraid. But yeah, I mean, it's yeah.
Because it seems to me that if you, it'd be interesting to know at least what kind of things you need to estimate to get your predictions.
Sure.
Correct.
Yeah. I mean, certainly household. For epidemics, I haven't really spoken about household models, but you know, their sort of household size distributions are important to include, and they're quite easily estimated.
Yeah.
But you really then, I mean, the models I've been describing here, I mean, they're just single type models, but you might want to include adults and children, different age groups, and different mixing for within and between households, and it soon becomes rather complicated. And there are studies, I know there's a number of studies using, trying to get such information and then put them into models.
So the problem of, it's partly a question for the audience as well, the problem of connectivity in a very general setting has been studied by Baylor and Svanto and Oliver Riordan. And I was wondering whether it's possible to use their techniques in this sort of slightly more complicated setting, but I mean, sorry, to prove things by a very general random graphs, homogeneous random graphs. Perhaps there's an audience perhaps for Baylor and Svanto, a question for Svanto.
But no, I was thinking about one important difference, because we had a method where we throw out small groups correspond to these households, but we do it randomly, so there an individual can be a member of several such groups, which could correspond to maybe organizations, work, and so on. But on the other hand, of course, in reality, it may also be natural to just have a partition into different households, and then it is a different type of model from ours. But I was just thinking about whether throwing out groups at random also could be useful for epidemic studies.
Yes, but in all these, the trouble is the underlying graph will be essentially mean field.
Mm-hmm.
I mean, so in the configuration model, what you have is essentially the total mean field with the edges added. So I don't expect any any resemblance to what happens in Hong Kong. No, it can't be, because that's based on the geometry of the place. It is based on where people live, and that is not taken into account by the configuration model at all.
But these global contexts are too simple.
Yeah, they are.
You have some kind of geometric graph, maybe.
Yeah, it has to be a geometric graph.
So there's
where all the connections are fairly short and.
So there's a paper, but I'm not sure exactly who the authors are, maybe Turova and Valier, and I'm not sure who else, perhaps someone knows, where they take a thing Z squared and do percolation Z squared, and then add some global edges, and then use your method to use your theorem, in fact, I think, so I don't know whether
that is, I think, closer to what could be in real life.
You can do that sort of thing, or if I understand it correctly, but then, and this sort of general methodology I presented for sort of analysing the final outcome of epidemics, I think will extend to that situation, if I understand it correctly, where you've got something like a geometric, locally you've got a geometric random graph, but you can't actually do, I can't actually do the computations to work out the size of a local susceptibility setting. You may be able to prove some theorems in a general sense.
Yeah, so in some sense it was lucky or perhaps designed. So in connectivity, then if your local graph is subcritical, when you use these bounded size components, and they're connected with probability proportion to the product of their sizes, and then that fits into this general mean field framework. Whereas perhaps here it's not quite. That doesn't seem to work as stated.
Well, it could be. Well,
perhaps once you've written to it, and this directed graph really is the same.
It is the same.
Because you're just looking at this component.
It is the same.
Okay.
To actually compute, if you want to actually compute numbers, is that, I don't think that's.
So you do the,
Well, the numbers are not quite the same, but if you let the number of vertices tend to infinity, you get the same.
But in a geometric random graph,
Yes.
if you want to look at the local susceptibility set, you may, I don't know about these things, but my guess is you can't actually get an explicit formula for the PGF of that susceptibility set.
I don't see why not. I bet one can.
More questions? I mean, I think that's an interesting point because it also shows that, I think one of your points was that people have extended models in various directions and they don't always necessarily align. Either the questions that people want to study or necessarily the techniques that people have developed, but it seems like there's some intersection. Other questions? Yeah?
I was wondering, I mean, you had this one kind of the R,
Yeah.
dependence of R on the kind of size of the component, it not being monotonic. And it's kind of peculiar but is there a particular reason why this would be the case?
I don't know, to be honest.
No.
I mean, I suspect it's an artifact of the way this network's been produced, I guess. There's,
Right, okay, so more an artifact than anything else. Yeah, that's what I would expect.
that's a guess. I mean, I don't know.
Yeah, I would think about where you use your R here, so to connect, preferably vertices of the same degree or almost the same degree, or the opposite thing, that maybe one could invent some other mechanism that would give similar result, but with some more spread out distribution of the degrees of pairs or pairs of degrees of the edges. So I didn't invent one immediately, but maybe people have studied such mechanisms also. Because I understand that this is a simplified model to get the degree correlation you want, but it would be interesting to look at more general models.
Yeah, well, I would have thought, that should be possible, I would have thought.
Any other questions? Just one quick last question. I'm sorry, Jane's not here for this one, but do you have a sense of how far ahead? So we have a general understanding that looking at more realistic or at least more complicated network models is relatively new. But do you have a sense of how far ahead all of this is from what people do in practice? I mean, if you think of something recent like what you mentioned, Hong Kong, or the spread of Ebola, or what have you, I mean, what do people actually do? You know, if you get a call from the World Health Organization, you know, how far behind are they in terms of what they're doing? I'm just curious.
Well, I never get a call from the World Health Organization, but I mean, I think what people tend to do would be to use sort of large-scale simulation models.
Yeah.
So, I mean, I think, these models would typically have households in the structure.
Right.
But they would have some rather detailed.
So they're kind of built in a bottom-up way. They're sort of mechanistic models that are built with an understanding from data.
Well,
but
I
they're
don't know
not
actually.
proper
I'm not
models.
sure that's necessarily the case, because there's some models which try to model everybody's down to everybody's last movement each day. You know,
Okay.
there's some are very highly complex.
I guess getting back to like Svanta's point, I was just thinking about how what you've been doing, it feels like, is beginning to try to close the gap between the models that perhaps would capture real world behavior on one hand, and then, you know, as you said at the beginning of the talk, models about which you can still manage to prove things. And I was just trying to get a sense of how big the gap is.
Yeah, I think I'll try to say one thing about this gap is, perhaps it's touched on it already, but all the models I've described, you're only really been able to get results out because you can approximate things by branching processes.
Yeah.
And I think for more realistic networks, that's not going to be the case, because you are going to come back. I mean, at some level here, there's always a branching process in the background which enables you to do analysis. So if there's...
If you lose that, then you might be
yeah,
stuck.
yeah.
Anything else? Let's thank Frank again. Thank you. Yes, be careful not to walk out.